Okay, good afternoon, everyone. We'll be talking today about light-matter interaction, or actually start talking about light-matter interaction, which is chapter 4. And before we do that, I will quickly review what we did last time, which is electromagnetic field quantization in resonators. And this is just the last part of that introduction on normal mode expansion and quantization, where we discussed structures with variation of the electric constant in space, which is of relevance to pretty much all of the resonators that we do today and that we will actually study in this class. And this is different from what you normally do in quantum optics classes, where people treat just free space between two mirrors, so sort of free space resonators or resonators with uniform medium. We're more interested in nanoresonators and microresonators, where you vary the electric constant in space. And in that case, you have to do normal mode expansion and quantization differently. We discussed that last time. Just the final comments on that. If you do expansion, normal mode expansion, you will still be able to expand in terms of the normal modes. But the spatial variation of these normal modes would satisfy orthonormality condition, which is somewhat different from like the regular definition of orthonormality in math, because you have this extra epsilon term here. So you basically start from spatial field profiles that are normalized in such a way that they're normalized to 1 with an extra factor of epsilon, but then they're orthogonal to each other if you look at modes at different frequencies. And the reason why this comes up is because the operator for electric field, when you have variation of the electric constant, is non-Hermitian. So we fixed that hermiticity problem by introducing a different operator, which is symmetric. And then we also proceeded by identifying basically by quantizing these harmonic oscillators that correspond to normal modes in the usual way. If you're interested in details of that, you can read the course reader. We will not really spend too much time on that here in interest of time, considering that we have a short quarter. But the bottom line is that when you proceed with the expansion, of course, the total Hamiltonian of the system would be sum of Hamiltonians corresponding to harmonic oscillators. So these AJ and AJ dagger are annihilation and creation operators for a specific mode J with the frequency omega J. And then you can also write electric and magnetic field operators in the form shown here, or here actually you already have spatial field patterns Fj, which are normalized in the way we showed on the previous page, normalized to 1 with an extra factor of epsilon. Or if you just simply run an electromagnetic simulation and you obtain an electric field pattern for some mode, EJ of R, let's say, for a mode with frequency omega J, and you can get that from finite difference time domain simulations or some eigenmode solver, then this Fj can be obtained by dividing that spatial field profile everywhere in space with square root of the mode volume times maximum of electric field energy density, epsilon E squared, and mode volume definition is the same one as we introduced before. So integral of epsilon E squared divided by maximum of epsilon E squared. And you can easily show that F's defined in this way satisfy orthonormality that we showed before, that basically they're orthonormal with an extra epsilon under the integral. So with that in mind, you can also write electric field operator for these arbitrary microresonators. Again, we're just discussing lossless systems here. We'll see how to treat losses later, but you can write electric and magnetic field operators. And here we care primarily about the electric field because we will look at the interaction between electric field and quantum emitters in the system. And electric field operator would look as shown here. So we just substituted expressions for F in terms of unnormalized fields into these expressions here. And here is what you have. So you have electric field operator, which will again be Hermitian. It's equal to its Hermitian conjugate. It has annihilation creation operators for a specific mode J. It has electric field patterns, which are basically obtained from classical electromagnetic simulation. And this is direct result, this EJ of R is electric field pattern that you obtain from any electromagnetic field simulator. You don't need to normalize it because this prefactor takes into account normalization. And this prefactor is very similar to prefactor that you would see in free space resonators because you are normalizing one quantum of energy, one photon, h bar omega, within the mode volume, optical mode volume, and basically you're obtaining some field amplitude that you would need to have in order to uniformly distribute that quantum of energy within one mode volume, right, for the resonator. So if you are looking into solving a specific problem, right? Let's say photonic crystal resonator, and we'll be solving problems like that. Let's say you look at this so-called L3 photonic crystal resonator. That resonator can have various resonances. These are electric field profiles of these resonances. They're quasi-normal. I mean, if you look at the overlap of their field patterns, they're pretty much normal. I mean, they're not exactly normal because with this relation, because there are losses in the system, but for sufficiently high Q factor, you can assume that they're pretty much normal to each other and orthogonal to each other. And then for each mode, you have to normalize it in this way, which means that you would just take electric field pattern that you obtain from the simulation, calculate mode volume for that field pattern, find maximum of epsilon E squared for that field pattern, and then just divide that electric field pattern with both V mode and maximum epsilon E squared. And that way you construct the electric field operator. And if you look at the expression for the electric field operator, it's obvious that the smaller the mode volume, the higher the strength of the operator. And you'll see today from the discussion that that also means stronger light matter interaction. So it's clearly important to squeeze the electric field inside of small mode volumes. Okay? So any questions about this? This was more or less a review of what we did last time. We'll start chapter 4 right now, but I just want to make sure you don't have questions about this part before we start cavity QED. Okay. All right, if there are no more questions, let's move on to cavity quantum electrodynamics. So this is what we call chapter 4. Chapter 4 basically studies light matter interaction in cavities or resonators. And we'll also discuss nonlinear optics in optical microcavities, which is very different in physics, but some of the results are similar, implying that you can increase the strength of interaction by increasing Q factor, reducing mode volume. So we'll teach that at the end of the chapter 4. And as part of the chapter 4, we will start today with introduction of the Jaynes-Cummings Hamiltonian, which is the Hamiltonian that describes light matter interaction between atom and the field. And you can also expand it to multi-atom system and the field. That would be Tavis-Cummings Hamiltonian, but we'll primarily focus on single atom and electric field. Then we will study strong and weak coupling regimes of cavity quantum electrodynamics. So we'll start today with the strong coupling regime where you observe Rabi oscillation, normal mode splitting, Drast and Baer states. Then we'll talk about weak coupling regime when losses dominate over this coherent interaction. And there we'll talk about Purcell factor, spontaneous emission rate enhancement in the cavity, how that affects lasers and quantum devices, and finish with discussion of nonlinear optics. So that's the plan. Again, this chapter studies cavity quantum electrodynamics. Cavity quantum electrodynamics is study of light matter interaction in cavities, right? And that, for this particular field, Nobel Prize in Physics was awarded 8 years ago to Serge Roche and David Wineland. David Wineland is a pioneer of ion-based quantum computing, and Serge Roche is really a pioneer of cavity quantum electrodynamics. He did a lot of seminal experiments by using atoms, microwave transitions in atoms coupled to large microwave cavities. And a lot of experiments that were subsequently done in the optical regime were previously done by Serge Roche in microwave regime. Again, physics of all of this is exactly the same. Whether you have optical transition or microwave transition, it would be pretty much the same. But of course, resonators are very different. And here we're looking into microwave resonators as opposed to large scale resonators. So if you're interested in learning more about this, there is a chapter 4 of the course reader online, of course. And there is also kind of expanded version focused on applications. This is a summary of the lectures I gave at the Les Houches Physics School a few years back. And it was published in a textbook, but you can actually download the free version online on archive and read it. There is a strong overlap with chapter 4, but it also contains a little bit more information. So now we're supposed to introduce this James-Cummings Hamiltonian, which is the central Hamiltonian describing interaction between atom and the field. And of course, we want to introduce the Hamiltonian. I mean, we want to kind of treat the system quantum mechanically, or we will not really be able to analyze all of the effects of interest. So in order to introduce quantum mechanical, this quantum mechanical Hamiltonian, we will start from a semi-classical treatment of the atom electric field interaction, and then basically map that Hamiltonian into quantum mechanical form. So classical treatment of the atom field interaction, which you've probably seen before, is that the interaction Hamiltonian, and this is basically just classical Hamiltonian interaction energy, is proportional to the dot product between dipole moment and electric field. So that just tells you what energy dipole would have in electric field, and this is completely classical, right? I mean, this is a classical electric field. If you align dipole with the electric field, it's in a lower energy state than if it's misaligned with the field. So that's kind of interaction energy between dipole and field. And this dipole moment can be calculated for a specific atom by summing up positions of all of the charges inside of the atom and multiplied by the vectors, position vectors of those charges relative to the nucleus, right? So it's a sum of Qi, Ri for that atom, and E is the classical field. So that's completely classical treatment. And if you are interested in just transitions of a specific electron in the atom, and of course atom can have many charges in a nucleus and also many electrons in different shells, but if you're interested in a so-called single electron atom, meaning transitions of one specific electron in the outer shell inside of the atom, you can look at it as a single electron atom and just look at the dipole moment corresponding to that specific electron. So then the whole dipole moment would be, instead of this whole sum, you just can write minus ER times dot product with the electric field, right? And that's also applicable to the artificial atoms. And of course, single electron atom is hydrogen, but you can also apply this model if you are looking at specific transitions of one electron in the atom. So that's a classical treatment. I mean, this is nothing new. You've seen this before. Dipole moment times electric field gives you interaction energy. But that's not what we really need. We need quantum mechanical Hamiltonian describing atom field interaction, which means that this interaction Hamiltonian has to be mapped to, has to really act on the eigenstates of atom and eigenstates of field, electromagnetic field. So that means that this electric field here should not be classical electric field. It should be electric field operator. And this here also, this dipole representation, I mean, this dipole has to be some sort of operator acting on the eigenstates of the atom. So that is not this classical treatment, but we'll now map it onto a Hamiltonian that acts on atomic eigenstates and the field, eigenstates of the field. So for this purpose, we will look at the two-level system, right? Just look at the two specific levels with the inside of the atom. And of course, atom can have many energy eigenstates and many levels for a particular electron. But in experimental case, or in real life, you generally don't care about all of those transitions. You will only care about the transitions that are nearly resonant with the driving electromagnetic field, right? So you can look at as many, you can have as many transitions as you like, but you will just consider here in this two-level system, the one that is resonant with your driving field. And driving field frequency is omega. So h bar omega is the energy of the driving photon, and transition frequency is nu here, and we assume that omega is pretty much equal to nu. And all the other transitions are off resonance, so they don't really matter. And we can model this atom as a two-level atom with ground state, G, and excited state, EX. And again, this atom doesn't have to be necessarily a neutral atom or ion, something in vacuum. As you'll see in a moment, it could also be artificial atom, impurity inside of semiconductor, such as color center, you know, in diamond or silicon carbide, or quantum dot, which also has discretized energy levels. Anything that would basically discretize energy eigenstates for the system, okay? And you pick two levels, and that's your two-level system. Any questions? Okay, so this is our two-level system. two levels that we're picking that are resonant with the, or nearly resonant with the driving field, right? And transition frequency is nu. So this is the eigenstates for the atom that we care about are G and EX, okay? So there are two eigenstates. There are many more eigenstates, but we will not really care about them because there is no, with this particular interaction, we can never bring the atom into any of those eigenstates. So it's only the basis consisting of two energy eigenstates for the atom. And for the field, energy eigenstates would be Fock states corresponding to this particular field. Okay, so we want to put this Hamiltonian into the form that acts on two eigenstates of the atom, which are G and EX, and Fock states for the field. And once we do that, we will have interaction Hamiltonian in James-Cummings, interaction term in James-Cummings Hamiltonian.
I have a question now.
Yeah, sure, you should.
Eigenstates, you're plugging is a Fock state, but you have an operator called R. But the Fock state doesn't have any information on the spatial.
Yes, so that term only affects the atom. So this term, as you see when we're transforming it into something that acts on atomic and field states, this part is not really, I mean, acting on the field. And you have to also keep in mind that this is much smaller than the electric field amplitude. So this is just the scale of the atom is much smaller than the variation in the electromagnetic field. So from the perspective of the field, this is very small, right? And this operator R is not really like acting on the field, but the alignment between this dipole moment and the field will matter. Okay? You will see in a moment when we're transforming it, yeah.
So you don't extract any information from Fock state of the position.
From the Fock state, you don't extract the information about the position of the atom, you mean? But the overlap between your field pattern, classical field pattern, and your atom will be important in defining the strength of the Hamiltonian.
I think I know.
Yeah, so wait a few slides and then you will see what we're talking about, okay? Yeah, because that's exactly what we will be doing right now, okay? So the total Hamiltonian of the system will be sum of three terms, right? So what do we have? We have atom, two-level atom, we have electromagnetic field, electric field, and we have interaction. So how do we represent these three terms? We have interaction Hamiltonian described as dipole moment times electric field. We will kind of transform that into something that acts on atomic eigenstates and Fock states, but we can easily write atomic and field Hamiltonian, right? So those are Hamiltonians describing non-interacting atom in the field. And for atom, atomic Hamiltonian can be written in few different ways for atom, for two-level atom. I like this particular representation. You can write it as, if you assume that the energy level 0 is between ground state and excited state, then the excited state has energy h bar nu over 2. Ground state is minus h bar nu over 2, and the choice of 0 is arbitrary. It doesn't matter. It's just a shifting 0 relative to the two states. And in that case, you can write that the atomic Hamiltonian is h bar nu over 2 times the population operator, which is the projection onto excited state minus projection on to the ground state. So you can easily see that when you apply this atomic operator onto excited state, that the excited state is the eigenstate of the atomic operator with eigenenergy plus h bar nu over 2. And when you apply it to the ground state is an eigenstate with the energy minus h bar nu over 2. And that's because excited and ground states are orthogonal to each other. If you took quantum mechanics, applied quantum mechanics, you may have written this exactly same Hamiltonian in terms of the fermionic annihilation and creation operators. It's exactly the same Hamiltonian. But I like this particular form with the population operator because it's more intuitive and it's easy to construct it. It's clear why you have to write it that way. Okay? And the field Hamiltonian, since we're talking about the interaction of a single cavity mode with the atom, is just quantum harmonic oscillator, where A and A dagger are annihilation and creation operators for that particular mode that is interacting with the system. So we have atomic Hamiltonian, it's just two-level system. Okay? We have field Hamiltonian, which is quantum harmonic oscillator. So field Hamiltonian acts on Fock states, right? Fock states are energy eigenstates for that field Hamiltonian. And this atomic Hamiltonian acts on excited and ground state. on the space spanned by excited and ground states, which are energy eigenstates of the atomic Hamiltonian. But the interaction Hamiltonian we only have in the classical form as the dipole moment times the electric field, and we now have to map it into something that would also act on atomic eigenstates E, X, and G, and the field eigenstates, which are Fock states. Is this okay? Okay, so how do we do that? How do we introduce quantum mechanical description of interaction Hamiltonian, which is a missing piece, right? So first, to introduce it in the form that would act on the atomic states, we can basically multiply both sides of this Hamiltonian with this unity operator, which is expanded. I mean, it's just a sum of the projection onto the excited state and the ground states for the atom. This unity operator, you can actually do, you've probably seen it if you do quantum mechanics, but you can write this by adding up projections onto all of the basis functions spanning a certain subspace. So if you do that, then you can multiply both sides of this interaction operator with this unity operator. And when you do that, this would only act on the first part of this expression, right? It would not really act on the electric field because when you're calculating these particular inner products that you have here, electric field would pretty much, and this is related to Yishu's question, would be constant over the scale where you're calculating these matrix elements, because electric field variation is much, much slower than the variation of the atomic eigenfunctions. Does that make sense?
Could you say that again?
Electric field variation in space is much slower. I mean, you're talking about optical frequencies. It's much slower than the variation, the rate of variation of the wave functions of your atom, right? So the size of your atom is much smaller than the size of electromagnetic field, right?
Yeah.
So when you're looking into all of these inner products, you are calculating basically overlaps of the atomic wave functions corresponding to the excited and ground states. And the extent of those wave functions is much, much smaller than the extent of the electromagnetic field, because you're just talking about single atom, right? That has scales much, much smaller than the scale of the field. Even for artificial atoms like quantum dots, these wave functions corresponding to excited and ground states are localized over the scales of 20 nanometers, which is still much, much smaller than the scale of your electromagnetic mode. So you can neglect the variations of electric field when you're calculating all of these integrals, right? And these matrix elements are just integrals. And this is why I told you to wait a few slides, because that's exactly what we're doing here. Does that address your question, Yushu?
Yeah.
So then that means that when you apply this unity operator on both sides of the interaction Hamiltonian, electric field would just be a constant term. And but you will still have to see how it acts on this dipole moment term, ER, right? So doing one on both sides of ER, which is a dipole moment, would give you basically these four expressions, because you have two here and two here, right? So you're multiplying operators, and you have ER in between. So when you multiply everything with everything, this is what you would obtain. You have these four terms. And these terms in the middle here would be just numbers. These are matrix elements that you're calculating when you're calculating overlap of the wave function corresponding to the excited state, for example, here, multiplied by ER, multiplied again by the wave function of the excited state, right? So this is like pretty standard calculation of the matrix elements, which we will not really be doing here. We'll just replace them with some constants, but I'm explaining you physically what they are. And if you do quantum mechanics, you must have calculated things like that. So for example, here, this one would be integral over the whole space of wave function corresponding to ground state of your atom. That's psi G complex conjugate times ER. This is term in between, and then wave function corresponding to excited state, which is psi EX over R, right? So you calculate that over the whole space. So when you finish all of these calculations, these would just give you some numbers, constants, which we actually call matrix elements, and we'll see what they mean, right? And they will be constants, but actually vectors, because you are calculating integral of this R vector over the whole space. So physically, they'll be vectors. So if those are just numbers, constants, these terms in the middle, right? You can pull them out. And then you are left with these terms that look like cat EX, bra EX, cat G, bra G, cat EX, bra G, cat G, bra EX. And physically, those terms are operators, because when they act on some function, right, some superposition of atomic eigenstate, they would just give you another wave function, another combination of atomic eigenstates. So they're operators, they're not numbers. So keeping that in mind, and by introducing these numbers labeling all of these matrix elements, we call them dipole moment matrix elements. I mean, whenever you see a term like this, where you have bra and then function and cat in quantum mechanics, that's called a matrix element, right? But these ones we call dipole moment matrix elements because they correspond to dipole moment of the atom between atomic eigenstates, okay? And we label them as mu ij for dipole moment matrix element between state I and state J, where I could be excited on ground state and J could also be excited on ground state. And as I said, these are just numbers, but they are also vectors, right? I mean, they're basically vectors, but constants that you obtain after calculation of these integrals, which is why we put arrow on top, and they're vectors because you are calculating basically matrix elements corresponding to vectors, to dipole moments that are vectors. These dipole moment matrix elements, I mean, if you had atomic wave functions, you could calculate, and I'm sure you calculated them in some quantum mechanics classes, but that's not what we will be doing here. We don't care, actually. I mean, there you can measure them. You take your atom or artificial atom, and you'll see when we look at the light-matter interaction that you can extract the value of this dipole moment matrix element from the measurement of the lifetime of the atom, okay? So it is for, you can get it from by measuring lifetime of a specific transition. You don't need to know your atomic wave functions to calculate it, okay?
So from the transition lifetime, how do you derive the dipole moment?
Yeah, so we have to derive the decay rate of the system, but the decay rate, radiative decay, depends on dipole moment squared. And even today, when we do strong coupling regime, you will see that the rate of interaction, Rabi frequency, depends on mu, right? So when you measure that experimentally, you can extract this value for the atom. Or when you just, pick an atom to do your experiment or quantum dot, you can either get the information about its lifetime, right? And from
how can
you measure it, and from that you can extract the value of this. You don't really need, the bottom line is that you don't really need to calculate these integrals.
How can you go from the scalar, which is the lifetime, to go to the vector?
It's not just that, it's proportional to mu squared, right? But there are other, fundamental constants that play a role there. I mean, that's next lecture, or maybe 2 lectures from now, yeah. Okay, any other questions? Okay, so we just introduced this dipole moment matrix element, mu ij, to label these numbers so that we have in the expression, right? So for example, this one here would be mu gg, right? And this one would be mu gex, right? So they're just corresponding to dipole moment matrix elements between different transitions that you can have, or different energy levels that you have in atom. And we also introduced 2 operators. We said that the rest here, apart from this matrix element, is an operator. So there are 4 different operators: ex, gg, exg, and gex, okay? These are operators. And they have different roles, and we will introduce labels for them. exg will be called raising operator, sigma plus, and gex will be called lowering operator, sigma minus. And the other 2, I mean, you can label them as sigma gg and sigma ee, right? Sigma plus or sigma, it's the same thing as sigma eg, and sigma minus is the same as sigma ge. The 2 remaining ones, sigma gg and sigma ee, are just gg and ex, right? So it's basically projections onto ground or excited state. Why do we call these 2 raising and lowering operators? Does that make sense?
Yeah.
Yeah, so if you apply raising operator onto ground state of the atom, what do you get? you move it to excited state, right? If you apply a lowering operator to excited state, you move it to ground state, right? If you apply a raising operator to excited state, what happens?
You get zero.
Zero, right? Nothing happens because we only work in a manifold where you have two states. It doesn't act on excited state because, of course, there are no other states in our model that you can bring the atom to. And what about sigma GG, for example? Doesn't do anything. If the system is in the ground state, it stays in the ground state. If it's in excited state, it's just zero, okay? But anyway, by using this notation, we can write ER instead of ER. We can write basically quantum mechanical description that acts on the atomic eigenstates, and it would be addition of these four terms. Okay, good. Any questions? So now we solved half of the problem, which is mapping interaction Hamiltonian into something that acts on atomic eigenstates. That's solved here. But we also have to map field Hamiltonian into something that acts on the eigenstates of the electromagnetic field. And to do that, we just write electric field operator, because electric field operator already acts on the Fock states, which are eigenstates of the electric field. Does that make sense? Right? So quantization of this interaction Hamiltonian is done once we introduce electric field operator, and we will write electric field operator for arbitrary resonator, which we introduced at the lecture last time, where you have this E of R, which is electric field pattern, right? I mean, of course, this is position dependent operator, but here we only care about the value of electric field at the location of your atom or artificial atom, which is why I wrote RA, right? That's the position of your atom. I don't care about the field very far from the atom, because the only thing that matters for the interaction is how field looks where you position atom. Does that make sense? Okay. So you write, I mean, even in a classical form, when you're calculating dot product, value of electric field at the location of the atom is what matters, right? So you write electric field operator at the location of the atom. So that value is from classical solution. You have annihilation and creation operator. This E hat is just the polarization of the field, unit vector describing the field orientation at the location of the atom. And this prefactor that we have here is what we derived last time. I mean, this is what we need to have in order to normalize the field, so that the fields are normalized with that extra epsilon term to preserve orthonormality, right? So you have mode volume, which is calculating as the normalized integral of epsilon E squared, normalized by maximum of epsilon E squared. You also have maximum electric field energy density, and h bar omega is just one photon of energy corresponding to field. So now if you introduce electric field operator, and keep in mind that this electric field operator is only for one specific mode of the field, okay? Arbitrary electric field operator that I wrote had a sum over all possible modes in the system. But if I have a two-level atom with specific transition, then it would only matter, I mean, in most cases, only one mode of electromagnetic field will be the one that can interact with that atom, right? So you don't really care about the electric field modes that have frequency very different from the transition of the atom, which is why I removed the sum here. But in some special cases, you may have two modes of electric field interacting with the atom, in which case you have to expand the treatment that we have here. For now, I assume that only one mode interacts, right? And that's the mode that I have here described in the operator. And also this is a description of the two-level atom. If you also have multiple atoms acting with the field, then you have to add up these dipole moments for all those different atoms, okay? And expand the basis, because there'll be ground and excited states for all atoms. And that brings you to that Tavis-Cummings Hamiltonian, which is just generalization of James-Cummings, but here we will only study two-level atom and one mode of electromagnetic field. Okay? It's quite simple to expand it. So when you introduce operator for electric field, right, we already have the description of this first dipole moment mapped onto atomic states, right? Now you have these four terms in that dipole moment, and you have two terms inside of the electric field operator. So when you multiply everything with everything, you will have 8 terms total in your interaction Hamiltonian, okay? So if we write that, there will be 8 terms, but you will see in a moment that not all of them matter, right? So before we do that, we have to kind of, before we complicate our life, we can actually neglect some of the terms in the dipole moment. So here are a few things that we can do. Well, first, these dipole moment matrix elements for excited or ground states, or between any state and itself, can be neglected, right? Why are, I mean, they're 0 unless you do apply some very strong electric field to atom, DC electric field, or change completely its wave functions. Why are they 0? It is 0 because when you look at these matrix elements and you look at the integral of ER, ER is an odd function relative to the nucleus, and wave functions corresponding to any eigenstate of the atom would be even or odd. So when you look at the magnitude square of that function, it would always be even. So overall, all of these matrix elements will be odd functions integrated over the whole space, which gives you 0. Okay? And again, if you have a quantum dot and you apply a very strong electric field and you completely change its wave functions so that they are not symmetric anymore, but they become asymmetric, really like start shifting system, then you may be in a situation where you start having non-zero terms for this, and you need to introduce them into the problem, and you cannot neglect them. But for great majority of problems, you can neglect them. So I will basically just remove them here. I will remove mu EE and I will remove mu GG. Is this clear? So if you look at the quantum, I mean, for example, quantum well, probably most of you have had quantum well. You look at you know how the wave functions of the quantum well look like, infinite quantum well, right? They're standing waves, right? And they're symmetric or anti-symmetric relative to the center of the quantum well, right? These integrals would be products of squares of those functions, right? Magnitude square of those functions that are just always symmetric, right? Times x. That's what it is for one-dimensional quantum well. And that's always 0. Unless you, again, apply very strong Stark shift and you obtain something like a triangular potential in the quantum well, then you are kind of localizing an electron towards one side of the quantum well, and these would not be 0 necessarily. But that's not really applicable here. Okay, so I neglect these 2 terms, which means that I have 2 terms in the atom and I have 2 terms in the field. So overall, I have 2 times 2, 4 terms instead of 8, okay? And when you multiply all those terms, this is what you would obtain. So we're not really doing anything special here. We're just multiplying these 2 terms with the electric field operator, which means that you have 4 total, right? Everything with everything. And these 4 terms are here, and then prefactor is what I had here as a prefactor in electric field operator. So let's analyze this here. What are these? Okay, mu EG, mu GE, and I wrote actually mu GE as mu EG complex conjugate. That's always the case, right? Because remember, what's mu EG and mu GE? These are inner products between, for mu EG, excited state and ER and ground state, and mu GE would be ground state, ER, excited state. So you can just apply complex conjugate and they're basically the same, right, with the complex conjugate. And then you have value of electric field or a complex conjugate of the value of electric field at the location of the atom, orientation of electric field. And then we have these terms, which are basically operators, products of, for example, raising operator and annihilation operator and so on. So what is this? What process does this describe? Raising operator and annihilation operator. What would that be physically?
Photon absorption.
Exactly, right. You absorb a photon, you annihilate a photon from a field, and you raise an atom, right? That's a physical process, right? What about sigma minus a dagger?
So it's the
photon emission.
Emission, exactly. So you have creation of a photon and lowering of the atom, okay? So those 2 are physical processes, absorption and emission. What about these 2? Sigma plus a dagger, what would that be?
Wouldn't those be physical processes? Because it's like One would be you're raising the state of the atom and at the same time emitting a photon from somewhere.
Absolutely. So you are raising the state, and then at the same time you are creating a photon. So it's not really energy conserving. And the same thing for this, when you are emitting a lowering an atom, right? Then you are also annihilating a photon. I mean, you can simply cancel out these two terms because they're not energy conserving, or you can also analyze them in the rotating wave approximation. For those of you who are familiar with the rotating wave approximation, it's the same thing as energy conservation. You just write them in the Heisenberg picture, and even you write them in Heisenberg pictures, and assuming that your atom is resonant with the field, these physical processes would be basically zero. I mean DC, right? Because at this A would oscillate with the frequency omega, and then sigma plus would be the frequency minus nu, right? So these two oscillating terms would cancel. But these two terms here that we're canceling by energy conservation would oscillate at the frequency 2 omega or 2 nu, right? And then by rotating wave approximation, you can actually remove them. But even if you're not familiar with rotating wave approximation, it doesn't matter. You can just cancel them because they're not physical. It's the same thing. Okay.
I have a question on derivation. Really quick. So we have the sigma EE from the equation above, but then we end up with sigma plus and sigma minus. And
yeah,
missing step.
Yeah. So sigma plus is the same thing as sigma EG, right? So I wrote that here a few slides back. I wrote that sigma plus is the same as sigma EG, right? It typically, I mean, the reason why I wrote it in two different ways is because you saw that we removed the terms that correspond to GG and EE because these dipole moments are zero, right? But I needed labels before I canceled these terms out for sigma EE and sigma GG, which is why I used sigma EG and sigma GE, right? But sigma EG is basically raising and sigma G is lowering, right? And I, not only me, but people in quantum optics prefer to use that notation with sigma plus and sigma minus because it's more self-explanatory. But I used the other notation until we got there and canceled the other terms. Okay, is that making sense? Yeah. Okay. So, yeah, sorry, I think I went a little bit. So here, right, these two terms are physical. These two we can cancel because they are not physical, right? And that's what we're doing here. We canceled these two terms because they're not physical. Or you cancel them by rotating wave approximation, which basically just leaves you with two terms. This is absorption and this is emission, right? And both of them have the same amplitude, which depends on the dipole moment matrix element dot product with the electric field. I mean, so E hat is the orientation of electric field at the position of the atom, right? That's all that matters here. And E is the electric field value at the position of the atom. And this is Hermitian. I mean, you can see the Hermitian conjugate of this is the same as the operator itself, right? So it's a Hermitian operator, which is good. Eigenstates are orthogonal and eigenfrequencies are real. So this is our interaction Hamiltonian placed in the quantum mechanical form. And if you look at it here, clearly this acts on eigenstates of the atom, which are E, X, and G, because operators sigma plus and sigma minus, they act on atomic eigenstates. And it also acts on states of the field because A and A dagger act on the Fock states. So few extra notes, right? It's a little bit of a messy expression. We can put it in a nicer form by introducing something that people call atom field coupling parameter, G, right? And that parameter is everything in this expression other than these operators. And I mean, just imaginary constant. So we group everything here as G. Okay, and again, this G is position dependent, but we only calculate it as the position of the atom because that's where we evaluate the atom. And that would be 1 over h bar, this term here, everything here, right? Times this dot product between dipole moment matrix element and electric field, right? And clearly here, if this is G, then this would be G complex conjugate, okay? if I introduce this atom field coupling parameter, then the whole interaction Hamiltonian can be written as I H bar, right? I didn't group I inside of G, and I introduced an extra H bar here, which is why I have H bar here. I'll explain the reasons for doing that, but everything else is grouped as a constant, and then the first term would be G complex conjugate, and then you have absorption, and then you have minus G, and then you have emission. Sorry, this is emission, and this, this is emission, this is absorption. Okay, so it's a Hermitian operator, right? Because these two terms are Hermitian conjugates of each other. The way we wrote it is with this imaginary constant, and of course, that's why you have a minus sign here to preserve hermiticity. In some textbooks, you can see it written as H bar times magnitude of G, and then you have absorption, emission and absorption terms with the plus sign between them, right? That's also Hermitian. And it's exactly the same form. Nothing will change. Those are two equivalent forms. Because every observable quantity in the system depends only on the magnitude of G. So here I introduce G in this way, right? And if you introduced it, grouped everything into real G, then it would be exactly the same thing, except that you would have a plus sign here. Because it has to be Hermitian. Okay? I prefer this form, and in most textbooks you will see this form, but for example, if you have Quantum Optics by Scully and Zuberi, then you will see H bar times magnitude of G, and then absorption plus emission terms with the plus sign in between. Completely equivalent. Don't worry about one being having a mistake. Okay, so we have interaction Hamiltonian, right? We also, of course, don't forget that you also have atomic and field Hamiltonians, which are describing the atom and field that are not interacting. And in this interaction Hamiltonian, atom field coupling parameter is everything other than these operators and H bar. This atom field coupling parameter G is often written as a product of three terms. G naught is the maximum value that it can have, so it's basically this prefactor of this. And then psi is the position dependent term, which is maximized when atom is positioned at the location of the maximum of epsilon E squared, right? So that's this term here, which reaches maximum value when you put your atom into the maximum of epsilon E squared, maximum of electric field energy density. And the third term, cosine psi, just depends on the polarization, orientation of the field relative to the atomic dipole moment. So reaches maximum value when the atomic dipole moment is aligned with the polarization of the field, electric field, at the location of the atom. Okay? So these terms psi and cosine reach maximum value of 1, which means that the maximum value that this coupling parameter can have is G naught. And G naught is in units of angular frequency because these are operators, absorption and emission, and units for the whole Hamiltonian have to be energy. And we have H bar here, which means G is in units of angular frequency, okay? Which is why we will also call something proportional to G Rabi frequency of the system once we analyze strong coupling regime, okay? So this is angular frequency. So when you look at this expression, when would the interaction between atom and field be the strongest? What do you have to do? Where would you have to put the atom? What do you have to do? Just look at this expression. How would you maximize the interaction Hamiltonian? You have to maximize G, right? If G is 0, there is no interaction, right? No matter how field looks like, right? So if you put your atom into the position inside of the resonator where electric field is 0, would there be any interaction?
No, it would be 0.
It would be 0, right? Because E of RA would be 0, right? So then the whole thing disappears. If you put it into the point where electric field is maximum, epsilon E squared is maximum, right? But you misalign atomic dipole moment from the electric field. You put dipole moment so that it's orthogonal to the electric field. What's the interaction?
0.
Zero, because also cosine, right? This term would be zero, right? The dipole moment, the dot product would be zero. So that tells you that you have to put the atom into the point where electric field energy density is maximum, right? Which is typically the same as the point where electric field is maximum, but I am, mathematically epsilon E squared has to be maximum. It's not generally the case for every arbitrary resonator. You also have to align dipole moment with the external electric field or they won't interact. And of course, you should do whatever you can to maximize G naught, right? Maximum value of G. So what would you do to maximize G naught?
You can reduce the mode volume.
Exactly, decrease the mode volume. Yes, so that's basically the reason why people bother making smaller resonators, because this whole thing, which is describing the interaction between atom and the field, scales as 1/square root of the mode volume. So if you squeeze if your extent of electric field is smaller, if you squeeze your field into a smaller volume, then you will have stronger interaction. Of course, you also need to be careful that there are no losses in the system. Keep in mind that we derived this for a lossless system. We'll see what happens when you lose photons from a resonator when quality factor is not very large, right? If you lose your photons before they can interact with the atom, then it's not going to be good, right? Very small mode volume is not going to help you achieve strong coupling regime, okay? So you have to keep Q factor as high as possible and reduce the mode volume as much as possible. So this is,
question on
yeah,
the
sure.
G
Yeah,
naught
of
on
course.
the previous slide. So it says G naught equal to 2 Rabi frequency. So
Yeah.
G naught has a dimension of frequency. What's the meaning of that?
What's the minimum?
What's a physical meaning of G? If you think that is have a dimension of frequency.
Yeah. So the physical meaning of G, you will see, depends on the regime of the interaction, right? If you're in the so-called strong coupling regime, which we'll start analyzing today, physical meaning of G is that, let's say you have only one atom in the field and there is no loss in the system, right? You put atom in the excited state, okay? And there are no photons in the field. What happens? What will happen? I mean, we'll analyze this from James Cummings Hamiltonian, but I'm asking you physically what will happen. I put the atom in the excited state. It's in a resonator. Resonator is not losing any photons. It has infinite Q. What happens? Atom decays, photon goes into a resonator, right? Okay?
Okay.
And what happens next?
And then just stay there forever.
Well, you also have absorption, right? If you look at the interaction Hamiltonian, there is emission and there is absorption. So photon goes into a resonator, but then atom can reabsorb it because it's not leaving the resonator, right? And then what happens next? Atom emits again a photon and then absorbs it, emits and absorbs, emits and absorbs. That's called Rabi oscillation. Physical meaning of G is that this frequency will happen, this oscillation, emission and absorption would happen with the frequency 2G. It's a Rabi frequency. But if you are in the big coupling regime, then the probability that the atom decays because it cannot reabsorb the photon leaves the cavity before it can reabsorb it, the probability that the atom generates a photon, goes into a ground state, is proportional to G squared also, right? That will be proportional to spontaneous emission rate, which we will do next week, right? That's why I told you that you can extract mu from the measurements of the spontaneous emission rate, because spontaneous emission rate is proportional to G. Okay? So just to summarize everything that we introduced so far, and then we'll make a brief break before we start analyzing the system using this James Cummings Hamiltonian. So when you have a coupled atom and field system, it will be described with the James Cummings Hamiltonian, and this is a single two-level atom coupled to a single mode of electromagnetic field. You will have atomic Hamiltonian, field Hamiltonian, and interaction Hamiltonian. Atomic Hamiltonian is just h bar nu over 2, population operator. So this is excited state minus ground state. This is field Hamiltonian for a single mode harmonic oscillator, and interaction Hamiltonian, what we just described, which has emission and absorption terms, and this is James-Cummins Hamiltonian. We'll see how we treat losses in the system later on. We'll also, and if you're interested in looking at two atoms interacting with the field, you need to add atomic Hamiltonians for the second atom. And if it's only one mode of the field, then basically atomic Hamiltonian is larger, and in the interaction Hamiltonian, you have to add terms for both atoms interacting with the field, right? So it's very easy to scale it up to multiple modes and multiple atoms. But in this course, we will stick to one atom and one mode. Okay, so let's make a brief break, and then after the break, we'll see how we can use this to analyze strong coupling regime. Of course, if you have any questions, I'm happy to pick them up.
I have a question about the interaction Hamiltonian.
Yeah.
Why is the A dagger and sigma minus flipped?
It doesn't matter in this case because they act on different spaces, right? But here I wrote them in the way that kind of represents a more physical process, because you will have to lower the atom in order to generate a photon, right? Looking from right to left, which is the order in which you act on something.
Yes.
And here you'll have to annihilate a photon in order to raise the atom. But doesn't really matter. I mean, this is just to be kind of physically more correct, but it doesn't matter because they act on different spaces. Yeah.
Okay, thanks.
Yeah. Are you attending Clio conference, folks, this week? Is that, or that's not so related to your field of research? Clio conference virtual one. I guess you can attend it for free. I guess a lot of people from my group are there. CLEO, no?
Sure.
Yeah. Yeah, because it's virtual, you can attend it for free. You just register and watch talks online.
Is there any approximation that we put in James-Cummins Hamiltonian?
Well, there are some things, that I already described along the way. I mean, of course, this one here assumes there are no losses. So we'll add losses additionally later on, right? Yeah. And we also made assumptions. I mean, one is related to the question that you asked, that the extent of atomic wave functions is much smaller than the electric field variation, scales of electric field variation, which in most cases is satisfied, but the only experimental condition where people had to introduce corrections for that was when they looked at quantum dots that have the scale of 20 nanometers, roughly, for excitonic wave functions interacting with some plasmonic modes that are also having very rapid variation of the electric field profile on the same scale of 20 nanometers. But the electric resonators, that's not an issue. So there was a work from Denmark looking into that. So the other actually approximation we made was that all the atomic wave functions are symmetric. And that's also the case pretty much always, unless you are, applying very strong electric field on the atom. Then you cannot neglect mu EE and mu GG, right? And we also made the assumption that transition in the atom is on resonance or almost on resonance with one specific mode of the electromagnetic field. If you have conditions that, multiple transitions are resonant with the field, or that you have multiple modes interacting with the atom, you have to, it's the same procedure, you just need to add extra terms. But 99.9% of the situations you can handle with this. Okay, so let's now just move on a little bit more, right? What we will spend the next few lectures on is starting from James-Cummins Hamiltonian and analyzing different conditions, right? And we will start with the strong coupling regime, which is what we were already discussing. That's the regime which is harder to achieve experimentally because, you have to basically bring the system into the situation where losses can be neglected, pretty much, right? And of course, that's much harder to achieve experimentally, but theoretically, that's the condition that's easiest to analyze because you neglect losses. Next week, we will talk about so-called weak coupling regime, where you cannot neglect losses. And in that case, you know, mathematical, theoretical treatment is more difficult because you have all these additional loss routes and loss channels, and you have to take into account interaction with modes other than the single cavity mode. So mathematical or theoretical treatment is more difficult, but experimentally, this is a condition that's much easier to achieve, right? Because loss dominates over coherent interaction. So we'll start with the strong coupling regime, right? Because that's the one that's easy to analyze theoretically. And this is the regime in which coupling strength G, right? So that's the same G that we have in the interaction Hamiltonian, it is in units of angular frequency, dominates over all the losses of the system. And losses of the system typically can be grouped in two categories. Always can be grouped in two categories. One is the cavity field decay, right? So that's your omega over 2q, right? Or omega over q if you are talking about the energy decay. This is telling you how fast you are losing a photon from the cavity. And the other is atomic dipole decay into everything other than the cavity mode. So if you take any atom or artificial atom or a quantum dot or color center, it will always decay. It has a finite decay rate, finite homogeneous line width. It has the finite decay time, right? And that decay could be a combination of radiative and non-radiative decay, especially for solid state emitters. So this decay is the decay into everything other than this cavity mode with which your atom is coherently coupled. In general, that's almost always just homogeneous line width of the system or decay that you would measure if you have an isolated atom. In some special circumstances, when you put a resonator, you do have strong interaction with one specific cavity mode, but you suppress interaction with some other optical modes or phononic modes. So you have to make sure that this gamma may be lower than the decay rate that you would obtain from an isolated atom without any structuring around. And we'll see examples of that, right? Which is why I'm trying to be very precise here. And I'm saying this gamma is the decay of your atom into everything other than the cavity mode with which it's coherently coupled. Okay? Right. So what happens there? And we already discussed this with Yushu in response to his question. You have your two-level atom, and these are supposed to be mirrors, right? And we are in condition when the coupling strength exceeds all these loss rates of the system, and we will even neglect them for a start, right? We assume that photon stays in cavity forever, and also that there is no decay into anything other than the cavity mode. In that case, Jaynes-Cummings Hamiltonian perfectly describes the system, right? It's only atom, two-level atom, one mode of the field, and interaction. So you have your atom, you have mirrors of this perfect resonator. You let your atom decay, you initialize it, you put it in the excited state somehow. You optically pump it or electrically initialize it, and you wait, right? What happens? It has to decay. Everything has to decay, right? It will decay and emit a photon into the cavity, right? But then this cavity is perfect, which means that the cavity will keep photon and atom will reabsorb the photon and go back to the excited state. And what happens now? Same thing, right? And so on. And that happens forever, right? So that's Rabi oscillation. So we'll prove that this is really happening, now and next time. So this is what is happening in time domain, and we'll see that initially you have no photons in the cavity. This oscillation happens with the rate 2g. It's very simple to show this. If you look at the system in spectral domain, you will see something called Rabi splitting. Normally, when you look at transmission through this cavity, you will see Lorentzian. We did that at the first weeks of the class. You see Lorentzian, which has line width proportional to 1 over q, or q factor of the system. So that's just an empty cavity. But if you put an atom into the cavity, and that atom is strongly coupled to the cavity, and you measure transmission through the system, you will see this splitting into two side bands and suppression of transmission and the cavity resonance. And we'll see that this is a frequency signature. I mean, separation between sidebands would be 2G, right? And you can kind of view this as sidebands of the original cavity resonance. And it's more complicated than this because there is a whole unharmonic ladder of dress states that is formed in this case. And we'll see what that means and some interesting consequences of that.
How can we go from the time domain picture and then see in the frequency domain picture there's a
we'll do that today and on Thursday. I mean, we'll start time domain today, but then we will do frequency domain picture next time, right?
Yeah.
You have to solve it separately, right? For time domain picture, we will just see time evolution of the wave function, solve time dependent Schrodinger equation. For frequency domain picture, we will have to basically solve eigenstates of the new Hamiltonian, which includes interaction. Okay, so there are two different kind of quantum mechanical, again, very simple treatment. I mean, very simple quantum mechanics problems, right? But you have to solve them separately. So we will go back and, you know, solve these problems from Jaynes-Cummings Hamiltonian that we have, right? So the whole point here is that we have atom interacting with the field. Separately, atom has atomic Hamiltonian, field has field Hamiltonian, but we also have an interaction Hamiltonian, which is Jaynes-Cummings Hamiltonian, right? Which we just introduced at the beginning of the lecture today, the first part of the lecture. So we have to solve for the system that consists of atomic, field, and interaction Hamiltonian. And first we will solve for Rabi oscillation, which is time domain picture, okay? And probably don't have time to solve for everything today, but we will start. I mean, that's kind of really just solving solution of the time-dependent Schrodinger equation. So when your atom and field are not coupled at all, right? Atomic eigenstates are Ex and G, right? And field eigenstates are Fock states and photons in the field. So if atom and field are not coupled, what are the eigenstates of the whole system consisting of atom and field that are decoupled from each other? You just need to write tensor products of atomic and field states, right? They're decoupled from each other, but you have to combine atomic and field states, right? So these energy eigenstates of the system where atom and field are decoupled, which is described with a Hamiltonian that has only atom and field, no interaction, right? You turn the interaction off. Energy eigenstates of that would just be combinations of the atomic and field eigenstates. For example, you have Ex, which is atom in the excited state, and N photons in the field. And that is an energy eigenstate of this Hamiltonian without interaction. H0 is just atomic plus field Hamiltonian, corresponding to the energy, which is a sum of the energy of the atom plus energy of that field. Does that make sense?
Yeah.
Right? That means they're just decoupled. You just combine two separate problems. Gn plus 1 is also an eigenstate of the system, and this would be the energy of that state, right? And of course, any arbitrary Ex and then arbitrary integer J or G and arbitrary integer number of photons J2 would be energy eigenstates of the system. But I'm only writing these two here because if I assume that I initialize the system in the state Exn initially, right? At time 0, I put the atom in the excited state and I have N photons in the cavity. By energy conservation, that system will never go into the state Gn plus 300, right? It can only go into state Gn plus 1 because atom is resonant with the field, right? So I don't really need to worry about anything other than these two energy eigenstates. Does that make sense?
Yeah.
Right? But any combination of Ex, G, and N is an eigenstate of the system. So here is the illustration of that. You know, Exn means you have N photons in the cavity initially, and atom is in the excited state. Of course, we still assume that the transition of the atom is resonant with the field. Nu is equal to omega, or roughly equal to omega. And if atom decays, it goes to state G, and then you will have one extra photon in the cavity. So that could be coupled to Gn plus 1, right? Okay. And of course, N could be 0 or could be 100. I mean, I can start with different number of photons initially, then that would lead to different results. But if I start from EXN, I can only couple it to GN plus 1. So these are energy eigenstates of the system without interaction. Now you take the knob, right? Then you crank up G, interaction term, right? So now that's a different situation. What are the energy eigenstates of that system with interaction? They're not going to be the same as these eigenstates. These are eigenstates of the system without interaction, and we'll find eigenstates of the system with interaction next time. So these are not energy eigenstates anymore, but I can still try to solve the problem using the basis of the original eigenstates of the system without interaction. Because it's same system, they're still a valid basis, right? They're not energy eigenstates, but they're a basis that I can use to solve the problem. So to solve the problem, I will just expand the solution for the wave function psi in terms of the original eigenstates of the system, which are EXN and GN plus 1. And then these coefficients, multiplying them will be time dependent in the general case. And I'm just pulling out here rapidly varying term, which is e to the minus I n plus 1 omega t, right? This term here is basically coming from the dominant term in the eigenenergy of these two states. If nu is equal to omega, this is exactly the frequency or energy that these two states would have. Okay, and you don't have to take it out. It just makes CEN and CGN plus 1 slowly varying. You can solve the problem even if you don't do this, but it kind of makes solution a little bit easier if you pull it out this way. Again, that's just math, it's not physics. So wave function of the system, I'll try to solve it in terms of, expansion, in terms of the basis of the original system without interaction. And of course, the basis of energy eigenstates of that system has infinite number of terms, but I only take into account 2 that can be coupled by this interaction for the reasons that we already explained. I don't need to care about Gn plus 300 because I'll never be able to bring the system into that state. Right? It's only EXN and GN plus 1 if you start from one of these two states and the field is resonant with the atom. And in order to find these coefficients, you have to solve time-dependent Schrödinger equation, which is written here. Hamiltonian of the system applied to psi is the same as IH bar d psi per dt, where the full Hamiltonian of the system is atom plus field plus interaction. Okay? So that's the problem that we need to solve. And again, if you took quantum mechanics, you probably solved similar problems to this. You just plug in this expansion for the wave function here, and then you can cap it with bras corresponding to different eigenstates, and you form coupled system of equations. And there are all the steps of the process described in the course reader. If you're interested, I'm not really going to go through it right now because it is very simple to do it, right? But this is what you would obtain once you plug in this expansion into Schrödinger equation and then act on it from the left with EXN or GN plus 1. You will construct these two equations, coupled equations for coefficients CEXN and CGN plus 1, okay? And these two coupled equations, coupled differential equations, I mean, since you have only 2 unknowns, CEN and CGN plus 1, when you solve them, you will be able to find coefficients CEN and CGN plus 1. Delta here, small delta, is detuning between atom and the field. So if atom is exactly on resonance with the field, these first factors drop off, and then the system is even easier to solve, right? There is no first term. You just have that CGN plus 1 is proportional to time derivative of CEN, and CEN is proportional to time derivative of CGN plus 1. So how do you solve equations like this? You apply derivative, right? And then you combine them. So without detuning, you will just obtain equations where second derivative of one coefficient is proportional to that same coefficient times some frequency. But if there is detuning, you can still solve for it, but it will be a little bit more complicated. So without detuning,
what's detuning?
Detuning means how far in frequency, nu minus omega, how far in frequency atom is from the field, right? So atomic transition corresponds to certain angular frequency nu, right? So the energy of the transition is h bar nu, and energy of a photon in electromagnetic field is h bar omega, which is angular frequency. If they're exactly on resonance, then delta is 0. But you know, keep in mind, we're just solving it for when nu and omega are approximately equal, right? When they're far from each other, there will be no interaction, but they don't have to be exactly on resonance with each other. There is still interaction even when they're not exactly resonant, okay?
Okay.
So then when delta is 0, you remove the first term, you apply second derivative on both equations, you combine them, and you obtain these two second order differential equations, one for CEN, one for CGN plus 1. These are very simple second order differential equations. What are the solutions of these equations? They're homogeneous second order differential equations, right? The simplest ones. Oscillation, right? That's the one that always pops up in physics, right? So CEN and CGN plus 1 would be proportional to some cosine or sine of G square root of n plus 1t, okay?
Yeah.
So these, I wrote one as cosine, one as sine because of the initial condition, right? I mean, because of course the whole state of the system is a sum. We have to go back to that, right? Remember, wave function is, this CN is a coefficient next to EXN, and CGN plus 1 is a coefficient next to GN plus 1. So physically, what's magnitude CEN squared? Probability that the system is in the state EXN, right? And magnitude of GN plus CGN plus 1 is the probability that the system is in the state GN plus 1, right? So if you start from, if you initialize system in the state EXN at time 0, that means that CEN squared at time 0 has to be 1, right? So you pick that one as cosine, okay? So CEN squared is cosine squared, CGN plus 1 squared is sine squared, or you can just use trigonometric relations and write them as 1 minus cosine 2g squared n plus 1t, and 1 plus cosine 2g squared 2g square root of n plus 1t, right? So if you initialize the system in the state EXN, what's happening? Same thing as the cartoon that we showed, right? System starts from EX with n photons, decays, photon goes into the cavity. You have n plus 1 photons atom in the state G, reabsorb the photon, go back here, emit a photon, go back here, reabsorb a photon, go here, and so on. What's the rate of this?
2G.
2G. 2G square root of n plus 1, where n is what? Number of photons that you have initially in the system, right? So if you start from empty resonator, where n is 0,
yep,
rate is 2G. If you start from 9 photons, right? Or if you start from 8 photons, the rate would be 2G times 3, right? Square root of 9. So it depends on the number of photons you have initially. But of course, if you start with no photons in the cavity, which means vacuum state, the rate would be 2G, which is why 2G is referred to as the vacuum Rabi frequency. You started with vacuum. But if you don't start with vacuum, it's 2G square root of n plus 1. So if you start with vacuum, it's vacuum Rabi oscillation. If you don't start with vacuum, then it's higher speed of oscillation.
Is there any interpretation to explain square root of n plus 1? Why the more photon, the Rabi frequency is larger?
Because interaction is larger, right? I mean, because remember, you have, if you think about it classically, if you squeeze more photons into certain volume, right, you have larger local field intensity, larger energy. So when your atom interacts with the field, interaction is larger, which is why it's much easier to see this oscillation when you start with more than vacuum initially and photons, right? It's easier to exceed loss in the system.
So it's always times the electric field's energy density.
Yes.
Times the what?
Yes, exactly. That scales as the number of photons you put in the system. Yes.
Okay. Yeah.
So just to summarize this, of course, you know, when you start with system in the excited state and n photons in the cavity, you will see vacuum Rabi oscillation. Here we are plotting probability that the system is in the excited state, right? So if you just track that, it will be 1 initially and then go back to 1 after time scale that corresponds to this inverse of the frequency 2g square root of n plus 1, right? And always goes perfectly to 1 because system is lossless. You know, half cycle later, you'll have atom in the ground state and n plus 1 photons in the field, and then goes back and so on. If you have losses in the system, we'll see that later. It starts with excited state, but after the first cycle, since you have a finite probability of losing photon from the cavity, this probability never goes back to 1 exactly, because the chances of atom reabsorbing the photon drop off, right? We'll see that. And if the system is detuned, if atom is not perfectly in resonance with the cavity, I mean, we'll go through this later, but I just want to show you all the plots now. It is also different. I mean, for the tuned system, you perfectly go oscillate between probability 0 and probability of 1 for having system in the excited state. For the tuned system, it will not go perfectly to 0, right? If you start with 1. Okay? So we'll see that later, right? But you can still solve the system. Okay, so next time we'll go here, vacuum Rabi oscillation, and pick up from here. Okay? Any questions? If not, thanks folks, and I'll see you all on Thursday. Bye.
Bye-bye.
Goodbye.
Bye.
Thank you.
Thank you.